Hey everyone. So, we all know solar energy is this massive, incredible resource we have. But there's a huge problem hiding in plain sight: efficiency. Now, most of the big leaps in solar power come from really complex chemistry. But today, we're looking at a totally different angle: a seriously clever solution that uses simple mechanics and electronics to get way more juice out of every single sunbeam. So, what's the actual problem here? Well, just think about it for a second. The sun moves across the sky all day, right? But most solar panels? They don't. They're just stuck in one spot. That means they're only perfectly angled to the sun for a super brief window of time. The rest of the day, they're catching sunlight at a bad angle, which means they're losing a ton of potential energy. And this really drives the point home. On one side, you've got your standard static panel. It works, sure, but it's just fundamentally inefficient. On the other side, you've got the ideal setup: a panel that can actually pivot and tilt, literally following the sun from sunrise to sunset. And the difference in energy you capture, it's not just a little bit more, it's a total game changer. Okay, so let's dig into this core weakness, right? The big problem of a panel that has to just sit still while its main power source is moving all day long. And to make matters worse, the solar cells themselves are only about 15% efficient on average. I mean, think about that. That's the starting line before you even factor in the angle of the sun. So when you're already starting with a number that low, any little improvement you can make to how you collect that light makes a massive difference to the final power you get out. All right, so how would we make the panel smarter? Let's break down this awesome DIY solar tracker, which uses a handful of really simple components to create a much more effective system. And you know, this quote from the project's creator really says it all. The goal is simple, but it's powerful. Build a system that follows the brightest light in the sky to make sure the solar cells are always in the perfect spot to generate maximum power. It's not about changing the cells, it's about changing how we use them. Okay, to really get how this clever gadget works, we're going to use a simple analogy. Just think of it like a little creature. It needs senses to figure out what's going on, a brain to make decisions, and muscles to act on those decisions. So let's start with its eyes. First up, the senses. To see the sun, this system doesn't use a camera or anything fancy. It uses something way simpler and, honestly, more elegant: to find the brightest spot in the sky. So the system's eyes are these tiny little components called LDRs, or Light Dependent Resistors. And their job is pretty much right there in the name. They're resistors, but their electrical resistance changes based on light. Put simply, the brighter the light that hits them, the less they resist the flow of electricity. Now this is where it gets really clever. The system uses 4 of these LDRs, and each one is pointing in a slightly different direction. So they're basically in a constant competition with each other. The one that gets blasted with the most direct, intense sunlight is going to have the lowest resistance, and because of that, it sends the strongest signal. And that's exactly how the tracker pinpoints the sun's location. So the system has its eyes, but all that data is pretty useless without a brain to process it, right? So now let's look at the central command center of this thing. The brain of this whole operation is an Arduino Nano. It's this tiny, programmable computer, a microcontroller, that takes all the information from the LDRIs and decides what to do next. It's the decision maker, constantly analyzing the data and giving out commands. The Arduino's logic is just a simple but constant loop. It reads the values from all 4 sensors, it compares them, and it basically asks, okay, which one is the brightest? As soon as it has an answer, it calculates the exact movement needed and sends a precise command out to the muscles. Okay, we've got the senses and the brain. The final piece of our analogy is, of course, the muscles. These are the parts that take the brain's commands and turn them into actual physical motion, moving the panels to face the sun. So the muscles here are 2 different types of motors. There's a DC motor that handles the big horizontal rotation, turning the whole thing from east to west. And then you have some high-torque servo motors that handle the really precise vertical tilting, making sure the panel is at that perfect angle to the sun. And here's how that all comes together. The Arduino itself can't power the motors directly, so it sends its signals to a motor driver. You can think of it like a translator. The driver then sends the right amount of power to the right motor, causing the whole 3D printed frame to rotate and tilt until all the LDR sensors are reading a balanced maximum amount of light. Okay, so the panel is perfectly aimed. Awesome. But tracking is really only half the battle. You also have to collect the power effectively, and that means you need a smart wiring strategy. And this project actually uses both methods. 2 of the 6-volt panels are wired in what's called series. Think of it like stacking batteries on top of each other. The voltage adds up, giving you a stronger electrical push. The other 2 panels are wired in parallel, which is more like opening up extra lanes on a highway. You get more electrical flow or amperage. The end result is a really nice, balanced output of both voltage and current. So let's do a super quick recap of the core parts. We've got the Arduino brain, the LDR eyes, and the servo and DC motor muscles. A motor driver acts as the nervous system, a buck converter manages the power, and the whole thing is held together by a custom 3D printed skeleton. Simple parts, but a really powerful combination. So what's the big takeaway here? It's that you don't always need some revolutionary new technology to make a huge impact. This project brilliantly uses affordable, off-the-shelf parts to dramatically boost the efficiency of existing solar cells. It's just a fantastic example of how clever engineering and a little DIY spirit can solve a very real-world problem. And that really just leaves us with one final thought. This project tackled energy efficiency with just a handful of sensors and motors. It really makes you wonder, what other complex global problems are just waiting for a simple, ingenious, and accessible solution just like this one? Thanks for tuning in.